Okay, let's talk about some mathematical applications of complex numbers. Specifically, let's talk about complex numbers and roots of algebraic equations. Now, complex numbers actually got their start when mathematicians started considering roots of algebraic equations. We mentioned that before. Here's one particular example of an algebraic equation. Z to the n equals 1. Now, n is a parameter, it's fixed, so it could be 2, 3, 4, or 4. But z is a variable, and you want to solve this equation for z for fixed values of n. For example, when n equals 4, you have this equation, z to the 4th equals 1. Now, what are the complex numbers that solve this equation? Well, 1 to the 4th equals 1, so this one's okay. Now, if you think about it, minus 1 to the 4th is also 1, so that's okay. Think about it further, and I to the 4th equals 1. I times I is minus 1. Multiply again by I, you get minus I. Multiply again by I, you get 1. Okay? Similar for minus I. You can work that out yourself. So we found, without too much trouble, 4 solutions to this equation. Z to the n equals 1 when n equals 4. These 4 numbers are called fourth roots of unity. If I had z to the 5th equals 1, that would be fifth roots of unity, and so on. Okay, so let's skip these exercises. Let's go down. So we saw that there are 4 fourth roots of unity, and in fact, it turns out that there are n different nth roots of unity. And we'll show that in this proposition. The proposition says the complex number z is an nth root of unity, forget the s there, if and only if z satisfies the following condition, z equals cis 2 pi k over n, where k is an integer between 0 and n minus 1. Okay. So we're using complex polar form, and we're saying that z equals cis 2 pi k over n. So what does that mean? That means that the modulus r is equal to 1, and the argument, or angle, has the form 2 pi k over n, where k is an integer between 0 and n minus 1. So let's look at a specific example. When n equals 4, this equation gives what? It gives z equals cis of 2k pi over 4, because n equals 4. And k is an integer between 0 and n minus 1, so that means k can be 0, 1, 2, or 3. So if we plug these values in turn into this equation, you get cis of 0. If I put k equals 1, I get cis pi over 2. Put k equal 2, I get cis pi. Put k equal 3, I get cis 3 pi over 2. Work that out yourself. We convert that to Cartesian form. Remember that cis of theta is equal to cos theta plus I sine theta. If you work that out, I'll let you work that out yourself, you actually get these 4 numbers, 1i minus 1 minus I, which agrees with the result that we got up here. So it looks like we're in good shape. All right, so let's give a proof. Now, since we're talking about roots and powers, it's not surprising that we're going to rely on Dumont's theorem. So remember, we want to show that, let me just write it over here. We want to show that we have an nth root has the form cis of 2 pi k over n. That's what we're trying to show. And this k goes from 0 up to n minus 1. There are n values there, 0 to n minus 1. Now that's going to be, we want this nth root if and only if it has this form. So since we have an if and only if, we have to prove the proposition both ways. So let's start with the if. If means that z is a complex nth root of unity. Our goal is to show that z must satisfy the given formula. Okay, so this is our hypothesis, that z is an nth root of unity. All right, so z is a complex number. We can write it in complex polar form. So we can write z as r cis theta. Okay, r is the modulus, theta is the complex argument or angle of z. So we can plug this in to the equation that z satisfies. We have z to the n equals 1. That implies r cis theta to the n equals 1. All right, and then using Dumont's theorem, r cis theta to the nth power is r to the n cis of n theta. Okay, key fact there. Right. Now notice if we take the modulus of both sides, we and simplify, you actually can work this down to r equals 1. Okay, so the fact that z is an nth root of 1 means that its modulus must be 1. That's a definite implication. Right? So we have r equals 1 as a result of this hypothesis that z is an nth root of 1. And we can substitute that back into Dumont's theorem here. So this r to the n becomes 1. And I get cis n theta equals 1. So that's where I started right here. I get cis n theta equals 1. So let me continue. What does cis n theta mean? Cis n theta is cosine theta plus I sine n theta. Right? Now, in order for two complex numbers to be equal, the real part must be equal, and the imaginary part it must be 0. What's the imaginary part over here? Well, there's nothing here. So it's 0 times I, or I times 0, however you prefer to write it. So that means that cos n theta must be 1, and sine n theta must be 0. All right? Now, when is cos n theta equal to 1? Well, if you can do your circle, and cos n theta equals 1 only when theta is 0, 2 pi, 4 pi, etc. And sine n theta is equal to 1 is equal to 0 at all of those angles. So that means that n theta must be some multiple of 2 pi. All right, if n theta is a multiple of m times 2 pi, that means theta equals m times 2 pi over n. So all we did here was go through this algebra and then substitute back in. That gives us that our angle theta must be a multiple of 2 pi over n. All right, so notice this similarity between this result and what we want to get up here. Now, what's the difference? The difference is that here, k can only take these values, and here m can be anything. So how do we cut down from any value of m to these values of k? Let's see how that works. All right, so to recap, what we have is that z must be in polar form given by modulus 1 and theta as some multiple of 2 pi over n. All right. The point is that you know that an angle can be expressed in multiple ways. If I take an angle and add 2 pi, then I'll get the same angle. If I add 4 pi, I get the same angle. So what I want to do is show that these angles can reduce to angles where I have 2 pi k over n, where k must be between 0 and n minus 1. So that's the argument here. Theta equals 2 pi m over n. Now any fraction of the form m over n can be written as an integer part plus a fractional part. For instance, if I have 4 over 3, I can write that as 1 plus 1 over 3. Okay? And this numerator here is less than 3. Okay? So, and I give some other example. I have 28 over 6, right? What is that? Well, that's 24 over 6, which is 4, plus 4 over 6. I think I did that right. All right. So this we have an integer part plus a fractional part. This numerator is less than 6. The numerator is less than the denominator. And we can do that in general. It's just called reduced fractions. This is like, I guess you call this a mixed fraction. So this fraction m over n I can write as an integer part plus a fractional part where L and K are integers and K is less than the denominator. So it's between 0 and the denominator. Okay, so now I have my K, which is in the form that I wanted up here. Okay, K is between 0 and n minus 1. Here I have my K between 0 and it's less than n. That means that that's the same thing as saying K is between 0 and could possibly equal to, and whoops, sorry, could possibly be equal to n minus 1. Whoops. All right. Okay. All right, so if I plug this in, z equals 2 pi m over n. Here I have cis of 2 pi. Here's my integer part plus my fractional part. Now I know by the algebraic properties of cis that cis of a sum is the product of the cis's. So I can break this apart, cis of 2 pi L times cis of 2 pi k over n. That just gives me cis of 2 pi k over n. That means z equals cis of 2 pi k over n, and I'm done with the if part. Z must have this form cis of 2 pi k over n. Now for the only if part, we must show that complex numbers that satisfy the formula are also nth roots of unity. But you can just plug it in. Just plug in cis of 2 pi k over n, take the nth power, and you get cis of 2k pi, which is equal to 1, so I'm done. Okay, very good. Okay, so I should verify that, in fact, this gives me n distinct values, which is true because this gives me n distinct angles between 0 and 2 pi. And if I have two different numbers between 0 and 2 pi, that gives me two different angles. Okay? I'm going to skip down to this place here. This is on page, in my edition, it's on page 52. And so we've talked about complex roots of unity, and we've given a complex polar form. Now, when we represent these roots of unity in the complex plane, they have some very interesting geometric properties. So this example gives the 8th roots of unity, and we plot them on the complex plane. I think you should do this yourself to see how it works. And if I plot these 8 roots of unity on the complex plane, lo and behold, here's 1, 2, 3, 4, 5, 6, 7, 8. They all lie on the unit circle. We know that because the modulus is 1. But lo and behold, if I connect them, they form a regular octagon. Pretty neat. Mixing geometry with algebra with complex numbers. And in fact, this is a general property, as you'll show with these different exercises, that third roots of unity form a triangle and equilateral triangle, and so on. We have also some exercises here to explore the relationship between roots of unity and geometry. And here we talk about multiplication, and we're going to see what multiplication does to this hexagon that we've created with the roots of unity. We can also see what complex conjugation does to these roots of unity. Let's just think about that question for a second. If I do complex conjugation, what does that do to this? I said hexagon, sorry, it's an oxagon. Okay, what does that do to this octagon? Well, what's the complex conjugate of this number here? Well, I just flip it down over the x-axis, and it flips down over to this one here. That Greek letter is an omega. That omega, which is one of the 8th roots of unity, flips down to this other 8th root of unity, which happens to be the 7th power of the original root of unity, and it's also a root of unity. So you can see that complex conjugate corresponds to flipping over the x-axis, and actually it takes one root of unity to another root of unity. You can actually prove that algebraically. So I've mentioned that we have rotation, which corresponds to multiplication by a complex number, and flipping. So we have two types of operations. Suppose I rotate and then flip, or on the other hand, I could flip and then rotate. For instance, suppose I rotate 90 degrees and then flip. Well, that means that this 1 will go up to I and then flip down to minus I. But suppose instead that I flip first and then rotate I rotate 90 degrees. If I flip first, this 1 stays itself, and then rotate 90 degrees, it goes up to I. So you can see the order of flipping and rotation will affect the result. This is called non-commutative. Another word that we use this is non-abelian. Well, these operations on the complex roots of unity are non-abelian. It matters what order you do. You can flipping and conjugation and rotation. The order in which you do them affects the result. We can also prove some theorems in plane geometry using complex numbers. For instance, you can prove the law of cosines, which is a common law in trigonometry, purely with complex numbers. It's a very nice and elegant proof. I invite you to look at that, and we'll close this section with that observation.